Hi everyone, my name is Hamid Kalhori, and in this video I'm going to show you one of the most interesting observation or interesting testing in mechanical vibration and measurement. In this video, what I'm going to do, I'm going to just do a demonstration of a 4 degrees of freedom system representing the actually the bounce and roll vibration of a actually half-car rig. You know that in reality, if you assume that if you model a vehicle as a rigid plate, generally speaking, it does have 3 modes of vibration. Bounce mode, so if you assume that actually a vehicle is a rigid plate, so it does have bounce mode. And it does have another mode of vibration which is called as pitch mode, which is front to rear or rear to front, something like this. And it does have another mode of vibration which is actually left to right or right to left, which we call it as roll mode. In this test, what we do and what we do have is actually a system having both bounce modes and roll modes. So the bounce mode is just simply this mode of vibration, and the roll mode is just simply this type of vibration. However, in actually this type of vibration, we do have both bounce and roll modes at the same time. Okay, in this test, we assumed we model the system in this way that the mass of chassis and the mass of the actually the body of the vehicle is actually represented by this mass, which we call it as a spring mass. So the spring mass is sitting on is actually sitting on the tire. So this chassis and the body of the vehicle, it does include everything inside the body of the vehicle, such as engines, such as suspension system, and everything else. So it's actually represented by this mass. So the spring mass is sitting on another 2 masses. Here, this green mass, and also on the other side, another green mass. So these 2 masses represent the mass of tires. So now, so this structure, just assume that this is the front part of the vehicle. So this is the half car, which is the front half of the vehicle. So the spring mass is sitting on the spring masses using springs and dampers on both sides. And also, so the spring, the spring and dampers represent the stiffness of the suspension, the stiffness and dampings of the suspension system of the vehicle. And this green mass and also the other green mass, they do represent the mass of tires. And also these 2 masses are sitting on the ground, basically using another 2 springs, which they do represent the stiffness of the tires, which actually you can, you know that the stiffness of the tires could be changed by changing the inflation and some other parameters, such as the material of the tires and different parameters. But here we assume that basically the stiffness of the tires is fixed, and also there is no damping because we don't have any damper on spring masses for these 2 green masses. What we're interested in this test is actually to identify the natural frequencies of the system and to identify the damping ratios of the system for different modes of vibration. So the first mode of vibration here is just bounce mode. How we actually excite bounce mode? We use a crane. So this is the crane. This is the hook of the crane. We move it down, and then we lift the spring mass. We lift it up, and then we release it from center of gravity. And then by this, actually in this case, we are able to excite bounce mode only. For exciting roll mode, we move the crane to, for example, this side, and then we lift it up from this side. And then we release it, and then we can excite roll mode. But the point is that by this action, we excite both roll mode and bounce mode, because if you want to excite only roll mode, you need to keep the center of gravity. You need to actually make some constraint or something like that to prevent center of gravity to vibrate in vertical direction. Meaning that you need to basically keep the center of gravity here by some constraints, which we don't have such clips or such actually constraints here. And also in a vehicle, in most of the cases, it's very hard to actually only excite only roll mode without exciting bounce mode. And so here we do have such scenarios, bounce and roll mode together. But the point is that if you are going to just extract the damping ratios of roll mode only, then you need to do some signal processing and some mathematical calculations. I will show you what types of calculation you need to apply. So the sensors here are LVDT. In this experiment, we are using LVDT, or basically linear variable differential transducer, to measure displacement of the structure at different points. LVDT is a common type of electromechanical transducer that can convert the rectilinear motion of an object to which it's coupled mechanically into a corresponding electrical signal. LVDT sensors are readily available that can measure movements as small as a few millimeters up to several centimeters. We use LVDTs to measure displacement at 4 points. So for spring mass, we use two LVDTs. One, this LVDT attached to this point of spring mass, and another one attached to this one, attached to actually this point of the spring mass. Depending upon the type of LVDT, the measurement range of each individual LVDT might be different. So for the scenarios where the mass is added and the spring mass equilibrium point thereby shifts vertically downwards, the body position needs to be adjusted to ensure that the measured displacement during vibration does not result in a maxing out of the measurement range. Because an LVDT is a transformer, it requires an AC drive signal. A dedicated electronics package or signal conditioner is generally used to generate this drive signal, and also to convert the device's analog AC output to plus or minus 5 DC voltage. We also have another two LVDTs for, maybe it's not visible in the video, but it's just, we do have another LVDT here, which measures the displacement of the spring mass on this side, and another one on the other side. So we measure for the displacement or the vibration response of 4 points. To find the sensitivities of LVDTs and basically to convert from measured raw voltages to engineering units, we can statically calibrate the LVDTs. So basically what we can do, we use a gauge block and we put the gauge block underneath the LVDTs, and we measure the produced output voltage. And by knowing the exact value of the length of the gauge block, we can find the sensitivity of LVDTs. So we usually use a couple of measurements, and therefore we use a couple of different gauge blocks with different length to actually find the linearity of LVDTs, and also to actually take an average of different values to find a better and more accurate sensitivity. Let's just look at the problem from this angle. If I excite the system like that, so it's vibrating, so I give it an initial actually velocity and displacement. So it starts to vibrate freely, so we've got free vibration, and it dampens out quickly. But I excite both bounce and roll modes. This actually LVDT measures the displacement of this point. If you apply a logarithmic decrement to this signal, it doesn't make any physical sense. It doesn't give you the damping ratio of actually bounce mode and roll mode, or bounce mode or roll mode, because it's mixed. This signal includes both bounce and roll modes together. But having a look at this, so this diagram represents this structure. We do have a spring mass sitting onto another spring mass representing the mass of tires using actually spring and dampers. And here we've got just springs. So this is a spring mass. So because of bounce mode, it goes down here, and then because of roll mode, it starts to vibrate, to actually have a rotational vibration here as roll mode. So this is the actual displacement here, which the LVDT actually measures, is that displacement for this side and this displacement for the other side. So what we're interested in is just to measure XCG, the displacement of center of gravity, and also theta here. By doing some simple calculation here, you can find the relationship between XCG and X left sprung mass and X right sprung mass, and also you can find the relationship between theta and X left sprung mass and X right sprung mass. Meaning that X left sprung mass and X right sprung mass, they are dependent coordinates. So they are dependent on XCG and theta. Then meaning that once you do the once you collect the signals, then you need to do some simple calculations to convert your actually dependent coordinate into your independent coordinate, which are independent coordinates, which are XCG and theta. And then you can apply logarithmic decrement for to XCG and logarithmic decrement to theta to find the damping ratios for bounce mode and damping ratios for roll mode. Also, what you can do to understand this test and this system in more details, you can add some weight to the structure. For example, I can add now this mass to the structure, 5 kilograms. You can also add another mass to the other side of the structure. Now, by doing this, actually you are adding, you are changing the stiffness of the structure, and then you are changing the mass of the structure. And then by changing the mass of the structure, you are changing the natural frequency of the structure. And so by you can add more weights, and then you do the test for actually bounce mode or for bounce and roll mode. And then by doing some signal processing, you will understand the influence of adding more masses to the structure. When we add extra mass to the system, we are in fact changing the natural frequency of the structure. As you can see here, for the case of added mass, the period of vibration response is larger than for the case without added mass. So it means that the natural frequency of the system decreases. We do have an interconnected hydraulic suspension system. This actually system offers more advantages with respect to conventional suspension systems. It mainly affects the stiffness and the damping coefficient of roll mode relative to bounce mode. Because of the arrangement of the housing here, once you apply the pressure, it will actually changes the stiffness of the roll mode rather than bounce mode. This figure shows a schematic of the hydraulic circuit designed for our half-car rig. As you can see here, it includes a couple of chambers and some accumulators. So chamber 1, chamber 4 and accumulator 1 are connected, and as you can see, chamber 2, chamber 3 and accumulator 2 are also connected. In the accumulator, there are bladers with inner gas in them. So let's just focus our attention first on bounce mode only. let's assume the vehicle body is moving downwards, and so chamber 2 is compressed, causing the oil to flow out of it. At the same time, chamber 3 is expanded, resulting in no change in overall chamber's volume. In other words, no oil will flow into the accumulator, and so the gas in the accumulator 2 is not compressed or expanded. A little bit of change might occur due to the piston rod area. This makes the pressure P2 remain unchanged, and therefore no extra force will be generated. Same with the chamber 1 and chamber 4 and accumulator 1 will be observed. Okay, let's go through roll mode. In roll mode, chamber 1 and chamber 4 are compressed, and so the chamber volume is decreased. Therefore, oil flows into accumulator A1, and so gas in accumulator is compressed and its pressure increases. The pressure in accumulator to A2 also decreases, and so it results in extra force generation by the roll mode. You can try different pressures, different added pressures, different added masses to dig out further the effects of different parameters on the natural frequencies and on the mode shapes of the structure. Okay, I believe that's about it, and I hope that you enjoyed this video. Thank you very much.